In section 5.5, we're going to be looking at special cases of factoring. So before we get started, it's going to be important to write down your list of perfect squares. So we're going to be looking at 1 through 12. 1 squared, or 1 times 1, is 1. 2 squared is 4. Then 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. Obviously, that list goes on for forever, but if you really know perfect squares for 1 through 12 for right now, you should be good to go. We're going to be talking a lot about trying to identify perfect squares, so having this list handy is going to be helpful. So in problem number 1, I want to factor x squared minus 81. My a value is 1. I don't see a b value because I don't see an x term, and my c value is negative 81. So if I see nothing, that means that my b value is 0. So I want two numbers that multiply to give me 1 times negative 81, or negative 81, and adds up to give me 0, which might seem weird until I remember that 9 times 9 gives me 81. And since I want to multiply to be negative 81, if I make one of those 9's negative, negative 9 plus 9 gives me 0, and then I found my factors. So my answer here would be x plus 9 times x minus 9. In this second problem, things get a little bit trickier. I want to factor 25x squared minus 64. So if I make my AC chart, I want two numbers that multiply to give me 25 times negative 64 and add up to give me 0, because again, I don't see that x term. Negative 64 times 25 gives me negative 1600, which would be a lot to try to think of all the factors of. So we're going to skip this for now, and we're going to talk about a pattern that we're going to notice. So in some space in your notebook, we need to write down a rule for factoring a difference of two squares. If I have a squared minus b squared, I can write out my factors as a plus b times a minus b. And in this class, all we're really going to look at is when they're perfect squares. So when I can easily take the square root of both terms, that's going to be what I'm working with. So for example, if I was doing x squared minus 100, instead of making that AC chart, I could square root x squared, I could square root 100. Again, I'm noticing that 100 is a perfect square, so this will be a nice whole number answers. I could write this as x minus 10 times x plus 10. And obviously, I could flip-flop those two and write x plus 10 or x minus 10. So back to our original problem. Instead of trying to figure out all the factors of negative 1600, instead, I noticed that 25 is a perfect square and 64 is a perfect square. So using that rule, I'm going to square root both terms. The square root of 25 is 5, the square root of x squared is x, and the square root of 64 is 8. So my final answer would be 5x minus 8 times 5x plus 8. And knowing that rule, that's going to be a lot quicker than obviously doing that factor tree. Now, in our last example, we're going to look at four different equations to factor. We're going to see if we can easily factor by a difference of perfect squares. In example number 1, I can use the difference of perfect squares because 100's a perfect square, 1's a perfect square, and they're being subtracted. So I'm going to square root both. Square root of 100 is 10, the square root of x squared is x, and the square root of 1 is 1. So my answer would be 10x plus 1 times 10x minus 1. In our next problem, since I'm adding instead of subtracting, I can't do the difference of perfect squares. Even though 36 and 4 are perfect squares, again, I needed those terms to be subtracted to do that rule. In our next example, 3 is not a perfect square, so I'm not going to do that either. And finally, in our last problem, 121 is a perfect square, 36 is a perfect square. I'm subtracting them, so it's a difference of perfect squares. I'm going to square root each term, and I'll have my answer. Square root of 121, x squared would be 11x. The square root of 36 would be 6. So my answer would be 11x plus 6 times 11x minus 6.